All right, Chemistry 111, this is Practice Exam 1, and we're going to start by taking a look at the first question. It says, a concise verbal or mathematical statement of a relationship between phenomena that is always the same under the same conditions is referred to as a law. And I spoke about laws and theories in Chapter 1, and I explained how a theory is the why, but a law answers what, and a law is a very short and concise statement, and so this refers to a law. Let's take a look at number 2. It says, which one of the following is an example of a physical property? So we're looking for a physical property. Ice floats on top of water. Meat rots if it is not refrigerated. A silver platter tarnishes. Dynamite explodes. Gasoline burns. Well, you probably noticed that there's something in common in B, C, D, and E, and all of these are chemical, right? These are all representations of chemical changes or chemical properties. And so the one that represents a physical property is ice floating on top of water. So ice is less dense than water. It floats on top. The ice is not being changed into anything else. It's still water molecules. So that represents a physical property. Look at number 3. It asks us which one of the following represents a chemical change. So we're looking for something here where bonds are broken and bonds are formed. If we look at the first one, it says boiling water to form steam. So all that's happening here is you're taking water in the liquid phase and it's being converted to steam, which is water in the gaseous phase. You still have water. Whereas burning a piece of coal, that is a chemical change. You're taking those bonds and you're causing them to undergo combustion, or the material in the coal, it's undergoing combustion, so that's a combination with oxygen to form carbon dioxide, water, carbon monoxide, and other products. So that's a chemical change. If we just take a look at the last ones, mixing iron filings in sand at room temperature, the iron filings and the sand will both retain their properties. They will not change. Breaking glass, even though it's broken, it's still glass, so that didn't change anything. And heating lead until it melts, so that again would be an example of a physical change where you're taking lead in the solid phase and then you heat it up and you just end up with lead in the liquid phase, but you haven't changed anything about the properties of the lead. All right, well, let's move on. The next one just involves some memorization of prefixes, the SI prefixes for kilo and milli. So if we think about a kilogram with respect to a gram, in 1 kilogram there are 1,000 grams. So the SI prefix kilo represents 1,000, or 10 to the power of 3, which again is the same thing as 1,000. And milli, if we think of, say, in 1 liter, there are 1,000 milliliters. So milli represents 1,000th, okay? So this represents a kilo, and then a milli would be 10 to the minus 3, or 1,000th. And there we go. So the correct answer for this one is the first one, 10 to the power of 3 and 10 to the power of minus 3, again represents kilo and milli respectively. All right, the next one asks us a centimeter corresponds to how many meters? Well, this one, what we could do is just use dimensional analysis to solve the problem. 1 centimeter, and we could convert that into meters, and we know that in 1 meter we have 100 centimeters, like that. So now my dimensional analysis is set up. Centimeters are going to be eliminated, and I'm going to end up with 1 divided by 1,000, and I'm going to end up with 1 divided by 100, which gives me 10 to the negative 2 meters, and so my answer will be E, 10 to the minus 2 meters, just like that. Number 6 is the highest temperature ever recorded in Phoenix, Arizona is 122 degrees Fahrenheit, but we want that temperature in degrees Celsius. You see all the answers are in degrees Celsius. So you need to know the formula that temperature in degrees Celsius is equal to 5/9 times the temperature in degrees Fahrenheit, subtract 32. Then it just becomes a matter of plugging the numbers in. So you have 5/9 times 122, subtract 32. And when you punch all that in your calculator, you end up with the temperature in Celsius is being equal to 50.0 degrees Celsius, like that. And so our answer is 50 degrees Celsius. So again, you need to know how to convert from Fahrenheit into Celsius, and you also have to be able to solve for Fahrenheit given temperature in Celsius. So you need to be able to do those conversions. And of course, Kelvin as well. You need to be able to convert to Kelvin. All right, well, let's move on to number 7. Number 7 asks us, it says dry ice, carbon dioxide, it's solid carbon dioxide, changes from a solid to a gas at negative 78.5 degrees Celsius. What's this temperature in Fahrenheit? Well, just like I told you, we have to be able to convert from degrees Celsius into Fahrenheit, and this is, again, very similar to the last problem, but we need our formula, which is temperature in degrees Fahrenheit is equal to the temperature in degrees Celsius times 9/5, and then we add 32 to that. So we get our temperature in degrees Fahrenheit is equal to negative 78.5 times 9/5. Oops, let me fix my number 5 there. There we go. And then we add 32 to that, and then you get the temperature in Fahrenheit is equal to negative 109.3 degrees Fahrenheit. Okay, there we go. So close enough. That's the closest answer. All right, well, let's take a look at number 8. Again, another problem that deals with conversions. You have to know how many milliliters are in a liter. And it asks us how many milliliters are in 0.005 liters. So let's set that up using dimensional analysis. First, we'll start by writing what we know, 0.005 liters. We need to use some kind of conversion factor so that liters can cancel out, and we'll end up with milliliters. Well, if we had milliliters on the numerator, we could do that. Now it's just a matter of knowing that in 1 liter we have 1,000 milliliters. And you can see that the units of liters will cancel, and I'll be left over with units of milliliters. And so when I take that 0.005 and then multiply it by 1,000, I'll be left over with 5 milliliters, which is my answer, A. Next question asks us to express a number in scientific notation. We went over this in lecture, and if we want to convert 26.7 into scientific notation, since 26.7 is greater than 1, so we have 26.7. The easiest way to do it is to move the decimal place to the right like this. And so when we move the decimal place to the right like that, we end up with 2.67 times 10 to the first power. And 10 to the first power, right, if I have 10 to the first power, that's the same thing as 10. So I think that everybody can do this math in their head. 2.67 times 10 is 26.7. So our answer totally works out. But again, you need to be rock solid on being able to convert numbers into scientific notation. All right, let's take a look at another problem. Number 10, after carrying out the following operations, how many significant figures are appropriate to show in the result? So here's the question. We have 13.7 plus 0.027 divided by 8.221. Well, you need to know the order of operations, right? BEDMAS. And I know that some students have learned other acronyms, but this is the one that I know, which is brackets, exponents, division, multiplication, addition, subtraction. And so we're going to solve what's inside the bracket first, right? We're going to solve 13.7 plus 0.027. Now, since this is addition, we have to look at the number of decimal places in both of these numbers. 13.7 has 1 decimal place, and 0.027 has 3 decimal places. And so when we add those two numbers up in our calculator, we're going to round the answer so that it only has 1 decimal place. And when I do that, I still end up with 13.7. So I have 13.7, and now I'm going to divide that by my 8.221. Now I'm on to division, right? I'm doing a division problem. And so when I do multiplication or division, the number of significant figures in my final answer is going to be governed by the number of significant figures in each of these numbers. 13.7 has 3 sig figs, and 8.221 has 4 sig figs. So whichever one of these has the least sig figs, that is how many sig figs I will report in my final answer. Since 3 is less than 4, we're going to report 3 significant figures in our final answer. And when you punch that into your calculator, you get 1.67 being the final answer. And so, how many sig figs are in the final answer? And the answer is 3. because 1.67 has 3 significant figures. All right, let's move on and look at a problem that just deals with how many significant figures are in a number. We have a number that's given to us in scientific notation. If we want to figure out how many significant figures are in a number with scientific notation, we only need to look at the mantissa. This number, the 1.050. Well, we know that any number that's not a 0 is significant, so we know for sure that the 1 and the 5 are significant, but what about the zeros? Well, the first 0 here, this is significant because it's sandwiched in between two non-zeros. The last 0 is a trailing 0, but it follows a decimal place, and so it is also significant, meaning all 4 of the digits are significant. And so our answer is there are 4 significant figures in this number. Okay, question 12. How many significant figures does the result of the following sum contain? We have 8.520 plus 2.7, and when you tally all that up, you end up with 11.22 when you put that in your calculator. But remember that when we do addition, that our result can only have as many decimal places as the number that's being added with the least decimal places. Now the first number has 1, 2, 3 decimal places, but 2.7 only has 1 decimal place, and so we can only report our final answer to 1 decimal place. The number that follows the 2 is a 2, which is one of 0, 1, 2, 3, 4, and so it doesn't need to be rounded up. And so the final answer is actually 11.2 would be the final answer, and there are 3 significant figures in 11.2. Let's move on to number 13. In number 13, it says, give the correct number of significant figures in the problem below. Well, this one is just a matter of being able to punch this into your calculator and knowing how to use the scientific notation function. And when you take your calculator and you put in 4.5 times 10 to the power of 14 divided by 8.3 times 10 to the power of 8, what are we going to do to those exponents, 14 and 8? We're going to subtract 8 from 14. And so that would leave us with 10 to the power of 6 left over. But if we take 4.5 and we divide it by 8.3, we end up with 0.54. So it would be 0.54 times 10 to the 6th, but we want to express it as 5.4 times 10 to the power of something, and so the answer is 5.4 times 10 to the power of 5. Now again, the easiest way to solve this problem is simply by punching it into your calculator and solving it that way. All right, let's take a look at number 14. It says a barrel of oil contains 42.0 gallons. How many liters is this? How many liters is this? Well, we're going to need a couple conversions in order to solve this problem because we're starting with 42.0 gallons, but the conversion factor that we're given doesn't have gallons in it. It's got liters, and that's what we want to solve for, but it also gives us quarts, and we're not given quarts. Well, you should know that in 1 gallon, we have 4 quarts. And so if I was to multiply 42 gallons by 4, I would actually end up with the number of quarts. But that's not what we want to have. We want to have liters, and so I can use the conversion factor that I have circled in blue, that in 1 liter I have 1.06 quarts, like that. So now we see that quarts cancel, and I'm left over with liters as my unit. So when you punch 42.0 multiplied by 4, divide by 1.06, you should end up with a number that can only be reported to 3 significant figures, and it's 158 liters, like that. So some conversions you are expected to know how many quarts are in a gallon. All right, let's move on to number 15. Question 15, it says, what is the volume in cubic centimeters of a brick that is 4 times 2.7 times 8 inches total for each side? So what are we going to do? The first thing I would do is I would calculate the volume of the brick in inches cubed. And then I would take the number of cubic inches and I would convert that into cubic centimeters. So the volume of the block, so the volume of the volume of the brick. Sorry, it's a brick. Let me back up here. The volume of our brick is equal to 4.0 inches times 2.7 inches times 8.0 inches, right? Because a brick is going to have 3 different sides. or 3 sides with 3 different lengths. And when you punch all that in your calculator, you end up with 86 cubic inches. So 86 inches to the power of 3. Now what we're going to do is we're going to be able to convert that into cubic centimeters. And the conversion factor, which isn't provided here, and this isn't one that you need to know, but this is a practice exam, and I guess I just forgot to put it in here, is that you need to know how many centimeters are in an inch. And if you have that, you can solve the problem. And I'll just write it over here. We know that in 1 inch, there are 2.54 centimeters. So if I was to multiply 86 inches cubed by 2.54 centimeters over 1 inch, that's not going to give us our answer because, why? Because inches cubed and inches are not going to cancel out. But if I take that entire conversion factor and I cube the whole thing, well, then I am going to end up with units that will cancel. So let's rewrite this again. Let's take 86 inches cubed times, I'm going to have 1 inch cubed in my denominator. And if I take my calculator and take 2.54 to the power of 3, I end up with 16.4. So there are 16.4 centimeters cubed in 1 inch cubed. And now I'm set up so the inches cubed will cancel, and I'll end up with my final answer in centimeters cubed. Now I can only report this final answer to 2 significant figures because I have 2 significant figures here in the 86. And so when I take 86 and I multiply it by 16.4, I'm doing that right now, you end up with 1,410.4. But again, we can only report that to 2 sig figs, and so I'm going to use scientific notation, and I would report that as 1.4 times 10 to the 3rd power centimeters cubed is my final answer, and that is A. All right, let's move on and look at another problem, number 16. It says a piece of metal with a mass of 611 grams is placed into a graduated cylinder that contains 25.1 milliliters of water. And it raises the level of the water to 56.7 milliliters. What's the density of the metal? Well, you need to know the formula for density, which is density is equal to mass over volume. Now, we've already got the mass. It's 611 grams. But what is our volume? Well, you need to think about it this way. First, let's put in our mass, and let's talk about the volume. When we had our container, okay, our graduated cylinder, okay, it's got a certain amount of water in it. Okay, there's a certain amount of water in that. But then once we put the piece of metal in there, then we see that the water level increases, right? It goes from 25.1 to 56.7 milliliters. So that means the difference between those two volumes is the amount of space that the piece of metal took up. And so our volume is going to be calculated as such. We could say that our total volume is going to be equal to the final volume minus the initial volume. And that's what I'm going to use as my denominator. So let's plug in some numbers. Our final volume is 56.7 milliliters. Our initial is 25.1 milliliters, like that. And when you do the math and you use the correct number of significant figures, you end up with 611 grams divided by 31.6 milliliters, which ends up being 19.3 grams per milliliter. Now you notice that our answer is in grams per milliliter, and all the answers that were given are in grams per centimeter cubed. Well, something else you need to know is that in 1 milliliter, there is 1 centimeter cubed. So that means that a density reported in grams per milliliter is the same thing as a density reported in grams per centimeter cubed. And so this is our answer, 19.3 grams per centimeter cubed. Let's move on to number 17. It says the Hope diamond weighs 44 carats. Determine the volume occupied by the diamond, given that its density is 3.5 grams per centimeter cubed at 20 degrees Celsius, and it tells us that 1 carat is equal to 0.200 grams. All right, well, let's try to solve this one using dimensional analysis. I know I'm starting off with a diamond that weighs 44.0 carats, and I know that in 1 carat, okay, I have 0.200 grams. Well, you can see the way that I set up this first conversion factor is such that the units of carats will cancel out, and I'll end up with the mass in grams. So that would tell me what the mass of the diamond is in grams. But I want to know what the volume is, don't I? That's what I'm looking for. Well, I can use one more conversion factor, and that is the density, 3.5 grams per centimeter cubed. Watch how I'm going to do that. I know that I have 3.5 grams of diamond in every 1 centimeter cubed of it. So now you see that grams cancel out, and I'm left over with the units of centimeter cubed. So I'm left over with the volume of the Hope diamond. Now, how many significant figures should there be in my final answer? Let's take a look at this one in a little more detail. You can see that the number of carats has 3 sig figs. The mass in the conversion factor is 0.200, which is 3 sig figs. The 1 is an exact number, so that's infinite. So far we still have 3. But if I look at my density, 3.5 grams per centimeter cubed, the 3.5 has 2 significant figures. So that means that I can report my final answer to only 2 significant figures. And so I punch that in my calculator and I get 2.5 centimeters cubed as being my volume. Number 18. The escape velocity from Earth, or the speed required to escape the Earth's gravitational pull, is 2.5 times 10 to the 4 miles per hour. What is this speed in meters per second? And we're given the conversion factor for miles into meters. So there's 1,609 meters in a mile. Well, let's see if we can do this. Again, this is another problem that gets you to really flex your dimensional analysis strength. So let's start out by writing what we know. Always start with what you know. We have 2.5 times 10 to the 4 miles per hour. And we want to end up with meters per second. So that means we're going to convert the hours to seconds and the miles to meters, right? If you think about it that way, it actually simplifies it a little bit. Well, let's start by converting the miles into meters. And we have the conversion factor to do that. We know that in 1 mile, we have 1,609 meters. Look, my units of miles cancel out. If I was to multiply these two numbers, I would have units of meters per hour, but I want meters per second. And we know that in 1 hour, we have 3,600 seconds. And if you're wondering how I got that, well, there's 60 seconds in a minute and there's 60 minutes in an hour. So 60 times 60 gives you 3,600 seconds. And now you can see that the units of hours cancel, and I'm left over with meters per second. So everything is set up. I punch all that into my calculator. I'm going to report my final answer to 2 significant figures, and I end up with 1.1 times 10 to the power of 4 meters per second, just like that. And so the answer is C. Let's move on to number 19. It says, give the correct number of significant figures and the units to the problem below. We have 5.67 meters divided by 2.04 meters squared. Well, for the numbers, I'm just going to punch that into my calculator. And since 5.67 has 3 sig figs and 2.04 has 3 sig figs, I'm going to grab my calculator. I got it right here. I'm going to put 5.67 divided by 2.04, and I end up with 2.779 something. So I end up with this big number, which is 2.7794. I'm not going to write the whole thing down, but I know that I can only have 3 significant figures in my answer. And so I'm going to have 1, 2, 3 sig figs, but you see the number that follows this 7 is a 9. And since it's one of 5, 6, 7, 8, 9, I'm going to round up, and so my answer will be 2.78. Now all the answers said 2.78, so that one's kind of a giveaway. But for our units, we have meters to the power of 1 in our numerator. We don't put the power of 1 in, but I'm going to put it in here for instructional purposes. And what we're going to do is we're going to subtract the power of 2. So 1 minus 2. And if you're wondering what I'm doing, this is just some simple algebra. And so 1 minus 2 gives you negative 1. And so our answer is 2.78 2.78 meters to the minus 1. And you should be able to manipulate units like that for the exam. Well, let's move on and look at question number 20. It says here that Americans combined drive about 4 times 10 to the 9 miles per day, and their vehicles get an average of 20 miles per gallon of fuel used. For each 1 kilogram of gasoline that's burned, about 3 kilograms of carbon dioxide are produced. How many kilograms of CO2 are emitted into the atmosphere each day by cars in the U.S.? And it tells you that 1 gallon of gas weighs about 3.5 kilograms. So, in the end, we are looking for how many kilograms, right? We want to figure how many kilograms of CO2 are emitted into the atmosphere each day. Well, this is another problem where you get to really use your dimensional analysis prowess. But let's start out with what we know. We know that we're driving a total of 4.0 times 10 to the 9 miles per day. And we know that we use about 1 gallon of gas for every 20 miles. Okay, for every 20 miles. So now you can see that miles cancel, and I'm left with the units of gallons per day. And what we're trying to figure out is how many kilograms of CO2 are emitted in the atmosphere each day. So we're not going to get rid of the day. Okay. Anyhow, now I want to convert the gallons into kilograms of gas. So let's do that. And I know that in 1 gallon, I have about 3.5 kilograms of gas. Okay. And I got that right here, since 1 gallon of gas weighs about 3.5 kilograms. So now you can see that gallons cancel. I have kilograms of gas, but I know that for each 1 kilogram of gasoline that's burned, I'm going to release 3.0 kilograms of CO2. So let's use that. For every 1 kilogram of gas burned, I'm going to produce 3.0 kilograms of CO2. And so the units of kilograms of gas cancel. What am I left over with? I'm left with the units of kilograms of CO2 that are going to be released into the atmosphere every day. And so I punch all that into my calculator. My final answer will only have 2 sig figs, and it's going to give you 2.1 times 10 to the 9 kilograms of CO2.